In this and the following segment, we are going to discuss some really useful properties of the position and momentum operators. First of all, we are going to confirm that they are indeed Hermitian. Then we turn once more to their eigenstates and confirm that these are indeed orthogonal and suitably normalized. Next, we look at some very simple rules for the expectation values. Then I'm going to introduce the very instructive so-called translation operators. Which simply shift the position or momentum of a quantum particle. These four aspects cover some very general and useful properties of the position and momentum operators, and we can then employ them to give a very compact proof of the uncertainty principle. And learn more about the quantum states which indeed minimize the uncertainties in position and momentum, the so-called minimal uncertainty wave packets. And finally, we are going to extend these into so-called coherent states. And this piece here will indeed be the advanced part of our discussion. So let us start with the hermiticity of X and P. Well, quite generally, a Hermitian operator was defined to obey the following relation. So this is phrased in terms of scalar products, where at both sides we have complex numbers, just evaluated in different ways. And these two numbers should be the same for all possible states psi and phi. Now the scalar product that we base our discussion on is the following. It's this overlap integral given here. Where we simply have complex functions psi and phi that depend on an argument x, which we consider to be real. So for the position operator, we therefore require that the following two expressions are always the same. And we can see this by simply inserting our definition of the scalar product here. So we have this expression and this expression. And these are indeed the same because here we deal with numbers that we can multiply in any order. So we can write this also as given here. And finally, x here is real. So these expressions are indeed the same. Now this is probably not surprising, but it becomes quite interesting when we now look at the momentum operator. So we are going to use this definition here when we act at wave functions as a function of position. And then we need to compare the following two expressions. Which we can write again in terms of integrals. So this integral here, or this integral here. Now these are not immediately identical, so we will need to work on them a little bit. And we do so by integrating the second expression by parts. So we're going to integrate this expression here and then take the derivative of this part here. And so we first of all get some boundary term, and then another integral in which we take a derivative with respect to x, but now of this wave function psi star. And this boundary term we need to evaluate at the integration boundaries, which are plus and minus infinity. Now this looks promising because these two terms are indeed identical. Note that this complex conjugation here also acts on this minus I, which therefore becomes a plus I. So the only difference would be this boundary term. But now we need to invoke our physical boundary conditions, namely that the wave functions need to vanish at infinity. So this should become 0. Now this is indeed a little bit of a subtle point, because we have encountered some wave functions that do not vanish at infinity, and indeed this included the eigenstates of the momentum operator. And now we learn something very important, namely that we can use these functions only in integrals, and only when we then multiply them by another function that indeed vanishes at infinity. And this is indeed a very important part of the mathematical structure of quantum mechanics. Whenever we evaluate integrals, they must give us finite results. And an example of where this becomes relevant is the following setting, when we ask the question in which sense the position eigenstates or the momentum eigenstates form a basis of states that are orthogonal to each other and are properly normalized. Let us again start with position. So our position eigenstates, well, we denoted them as psi x naught of x, and we said that these are Dirac delta functions. And so if we now calculate the overlap integral or scalar product between two of these, we have the following integral. And this we can then evaluate in two different ways, because the delta function indeed just tells us what happens with these integrals. So this delta function tells us that the result should be this function here evaluated at x naught, so delta of x1 minus x naught. But we can also just interchange the two rows of these functions, and then we just obtain delta of x naught minus x1. And this is indeed fine. All that this tells us is that the delta function is indeed a symmetric function. Next, this indeed confirms that these eigenstates are orthogonal to each other, because whenever x naught is not equal to x1, then this expression here vanishes. However, when x naught and x1 are equal to each other, we get infinity on the other side and not just 1. And we will see that this is indeed consistent, but it also means that we should never really use this expression when it just appears on its own, but only if it appears itself in an integral. And an important example of this, which also confirms that this is all consistent, is the following. In any orthogonal normalized basis, we can write the identity operator in the following way. Namely just as a sum over all the basis states with these expressions here. And this should also apply for a continuous basis, such as the basis of these position eigenstates. And there the sum becomes an integral. And in here we have the corresponding position eigenstates, which for convenience I just now denote as x. So interpreting these wave functions here in terms of abstract states psi x naught, we are just now going to abbreviate this as x naught. And this should be an integral over all the possible states. So again, with integration boundaries minus infinity and plus infinity. And then we can write down the following identity. We can write any arbitrary state psi also as the identity operator times psi, and inserting this expression here, we now have this result here. And this now has simply taken the form of our expansion of our wave function in the position basis, where we would call the expansion coefficients psi of x. And now we can read off that these expansion coefficients should be given by this expression here. Now I just need to insert this notation from above here again. And this indeed holds for any wave function psi of x because of this specific form of the position eigenstates given here. So everything is indeed completely consistent. Just to give you another example, we could, for instance, now also calculate the square of the identity operator, so I times itself, and this would now become two integrals. Where I'm going to choose different integration variables. So this one here I'm going to call x prime. And now we have this scalar product here. So this becomes this double integral. As given here. But this is now just the delta function again. And this allows us to integrate over, say, x prime. Just telling us that here we should insert x. So we get rid of one of the two integrals. And what remains is this expression here, which is just the identity operator itself. But this is, of course, one of the very important properties of the identity operator, that it should simply square to itself. Let us turn to the momentum operator, which has the eigenstates as given here. So these plane waves that we have encountered before. So the corresponding eigenstates I'm just going to denote by p. And when we evaluate the scalar product between two such states, then we get the following expression, where there is a complex conjugation on the first of the two wave functions. And then we have the second one. So we have this integral here. Here we can combine the exponents. So we obtain this expression here. This we can integrate directly because it just involves an exponential function. And so we obtain this expression here. Which we have to evaluate again at the integration boundaries. And now we have a situation just as before, but now it's a bit more subtle because we really have a function that does not vanish at plus or minus infinity. And on top of this we have this factor here, which potentially can be infinite itself. Well, if p is not equal to p prime, then this expression will always be multiplied by another function that indeed vanishes at plus or minus infinity. And this allows us to really just set this to 0. But if p is equal to p prime, then we really have to consider this to be infinity. And this reminds us of the situation that we had with the position eigenstates. And just as there, the only consistent choice is then to set this to the delta function with the argument being the difference of the two eigenvalues, which are now p and p prime. Well, this looks a little bit like we are treating position and momentum on different footings, but we can indeed turn the role around, and this can be done by simply using the momentum wave functions. So this is this wave function here, which we obtain from any quantum state psi by the scalar product with a momentum eigenstate psi p. So this would be just this integral here. With a minus sign in front of this term here, simply because this is in the left entry of the scalar product, and then the wave function here. So this momentum wave function is indeed just the expansion coefficient in the momentum basis, which we can derive in the very same way as before, but now writing the identity operator in terms of this integral here with the momentum eigenstates. And then we conclude that the expansion coefficients should really be given by this expression here. So again, everything is consistent. And now we can use this to see how the position and momentum operators are acting on this momentum wave function. And this is indeed very easy for the momentum operator, because if we simply apply this to this expression for the wave function, then in here it just acts on one of its eigenstates. So here we can just replace it by this expression here. And then we can combine this with the momentum wave function to see that it simply has been multiplied by its argument. So we can say that in this basis, the momentum operator simply works by multiplication by its argument. So very similar to what we have seen for the position operator in the position eigenbasis. And now how does the position operator act in this basis? Well, for this we evaluate what it does to a state in the momentum basis, so work out the corresponding expansion coefficient after we have applied the position operator. And now this we can write down in any kind of basis. And it is most convenient to write this down in the position basis, because there we know how the position operator acts on the wave function. Namely, we can just replace it by x, because there it just multiplies the wave function by its argument. And now we can see that this is equivalent to a certain parametric derivative of an integral, namely this integral here. So this works out because this derivative with respect to p, according to the chain rule, just gives us some factors from whatever is multiplied by p in the exponent, some of which cancel just with this IH bar, and what remains is really just this x here. And now this integral here is of course just our momentum wave function. And therefore what we have in front we should interpret as the position operator in the basis of the momentum eigenstates. So in this basis, x corresponds to this operator here. And this is beautifully symmetric. It just looks like the momentum operator in the position basis up to the replacement of x and p and a minus sign in front of the I, which is missing in this operator here. But this is simply related to this minus sign here. For instance, we can now check that the commutator between these two operators is indeed just the same as before, because these operators always act on some functions on the right. And then we would apply here the product rule and just get a 1 from the derivative acting on here, and a PDDP for acting on the remainder. But this is just cancelling with this term, and so we again obtain IH bar. So we see that this missing minus sign here is indeed important to obtain the same commutator with the same sign. And again, everything remains consistent.